This is OwlUp, where learning happens in minutes, not hours. For a deeper journey, explore all our courses at owlup.co. Now, let's dive in. Welcome back to Chapter 5 of From Pixels to Predictions, where today we're diving into our episode on advanced object detection. In this session, we'll explore some cutting-edge techniques that are pushing the boundaries of how machines recognize and categorize objects and images. So, whether you're a seasoned developer or just curious about the magic behind the scenes, let's get started. Your car can spot a cyclist in the rain faster than you can blink, without seeing the cyclist at all. In one instant, it's just raw pixels. In the next, it's a labeled, boxed human on a screen. Somewhere in between, a silent debate decides, is that really a person or just a shadow? In 2012, detecting objects in a single high-res photo could take longer than brewing a cup of coffee. Today, the same task can finish before you finish a blink, on a phone chip barely warm to the touch. The leap wasn't just better vision, it was a rethink of how models search an image. Instead of exhaustively checking every possible spot, modern detectors learned to be selective and fast. Now the stakes are higher. A drone must find a distant truck in a dusty frame. An AR headset must track hands as they move. A factory camera must spot a single defective screw on a crowded conveyor. Detection isn't just, is there a cat, but how many, where exactly, and how confident are we? That's where today's advanced systems come in. Region-based hunters that carefully propose likely object zones, and single-shot sprinters that decide everything in one streamlined pass. An image isn't just busy or simple to these models, it's a battlefield of competing hypotheses. Is that long shape a skateboard, a bench, or a dog lying flat? Are those overlapping blobs 3 people or 1 person with bags? Advanced systems must juggle clutter, motion blur, tiny distant targets, and objects sliced off by the frame. In a crowded street scene, a single frame can contain dozens of such puzzles. The detectors that thrive here rely on huge benchmarks like MS Coco, clever training tricks, and architectures tuned differently for phones, data centers, and tiny edge chips. The first fork in today's detection pipelines is philosophical as much as technical. Do you carefully shortlist candidates, or bet on a single confident sweep? Region-based models lean into caution. They start by learning where interesting stuff tends to appear. Tight corners, textured blobs, shapes that look like they might belong to something solid. Instead of scanning the whole image at full detail, they propose a few hundred promising chunks. Each chunk then goes through a deeper, more expensive analysis that answers, what is this, and exactly how big is it? That second stage can afford to be meticulous, measuring boundaries, nudging box coordinates, because it's only focusing on a filtered list. This makes them strong when objects are tiny, overlapping, or half-hidden, like pedestrians behind parked cars or tools scattered on a crowded workbench. Single-shot approaches bet on speed and pattern regularity. They divide the image into a grid of candidate spots and ask the network to predict everything in one go. Whether a region holds an object, which class it belongs to, and how to stretch or shift a box to fit. Instead of handcrafted rules about box shapes, the model learns typical sizes and aspect ratios for things like trucks, cups, or traffic lights directly from data. Later variants refine this idea, stacking predictions at multiple scales so that small faces far away and large buses up close can be detected in the same pass. Transformers push this further by discarding rigid grids altogether. They treat detection as a set prediction problem. A fixed number of slots compete to explain what's in the image, each learning to specialize in different situations. Because attention layers can connect any region to any other, these models can reconcile tricky scenes where context matters, like deciding whether a small rectangular patch is a phone, a book, or just part of a table, based on relationships to surrounding objects and layout. Behind all of this sits a brutal training regime. Millions of gradient updates, heavy data augmentation, and loss functions that juggle class confidence, box overlap, and duplicate suppression, all tuned delicately to avoid missing what matters most. A delivery robot weaving through a warehouse doesn't just see boxes. It's running an ongoing negotiation between candidates. This cluster of pixels might be a fragile package, that one a human leg, another just a painted floor marker. In practice, detectors get tuned very differently depending on who's hiring them. An e-commerce giant might favor a configuration that never misses a product, even if it occasionally hallucinates an extra box on a shelf. An autonomous vehicle stack will often flip that trade. It's acceptable to ignore a stray plastic bag, but not to wrongly mark a traffic lane as clear. In factories, detectors are pushed to extremes on scale. One system spots millimeter-wide cracks on turbine blades, another tracks thousands of parts per minute on a conveyor. Training there might oversample the most expensive failure modes, missing a crack, while largely ignoring cosmetic noise. Your challenge this week: pick a real scenario, cars, drones, retail, medicine, and map which detection errors would be most costly and how you'd bias the system in response. As detectors spread from phones into street cameras, hospital robots, and home assistants, they quietly start shaping policy and behavior. A model that flags every suspicious object in a subway, for instance, can jam security like a smoke alarm hung over a toaster. Future systems will need dials, not just on speed or accuracy, but on values: whose safety matters most, whose privacy is protected, and who gets to tune those thresholds. As detectors mature, they'll start negotiating with other systems, planners, maps, even language models, before anyone acts. Instead of a lone verdict, you get a conversation. I see something small, fast, and low confidence. Like a cautious investor diversifying a portfolio, future stacks will hedge across sensors, models, and viewpoints to balance risk and opportunity. Before next week, ask yourself: 1. If I had to deploy a real-time object detector tomorrow, what concrete trade-offs would I make between YOLO V8, faster R-CNN, and DETR in terms of latency, hardware limits, and the kinds of objects I care about? 2. Looking at one real dataset I have, or can grab today, like COCO or Open Images, where do I most expect my model to fail? Tiny objects, occlusions, unusual aspect ratios, and how would I adjust augmentation, anchor sizes, or feature pyramid levels to handle those cases? 3. If my current evaluation only uses map, which additional diagnostics, per class AP, size-based AP, confusion matrix, qualitative error inspection, could I run this week to uncover at least one non-obvious failure mode in my detector? This was OwlUp, your daily step forward. This series continues with more chapters on OwlUp.co. Visit OwlUp.co to access the complete course and continue your learning journey. See you there!